On November 5, 2018, something disappeared around Voyager 2. There was no flash, no shock wave struck the spacecraft, no camera captured a wall moving past its antenna. The stars looked exactly as they had the day before, yet inside one of the probe's surviving instruments, the electrical current produced by particles flowing from the sun suddenly collapsed. For more than 41 years, Voyager 2 had traveled inside a vast invisible atmosphere created by our star, even beyond Neptune, even where sunlight had weakened into a distant glow. The spacecraft remained immersed in the solar wind, a stream of charged particles expanding outward from the sun in every direction. Then the flow stopped. The 3 plasma detectors facing the sun registered almost nothing. Particles born inside the heliosphere fell away. Higher energy cosmic rays arriving from the galaxy rose sharply. The magnetic field became stronger. Every major instrument capable of identifying the transition began reporting the same impossible conclusion. Voyager 2 had crossed the heliopause. It had entered interstellar space. But what happened next was not the clean escape scientists had imagined. The probe did not pass through a simple shell and emerge into calm, untouched space. It found plasma compressed on both sides of the boundary. It found material outside the heliosphere that was warmer than models expected. It detected solar particles leaking into the interstellar medium. And its magnetometer confirmed something that had already confused researchers when Voyager 1 crossed 6 years earlier. The magnetic field outside the solar bubble was pointing almost the same way as the magnetic field inside it. The border was supposed to separate 2 different environments. Instead, the 2 sides appeared connected. NASA Jet Propulsion Laboratory, JPL. The first correction is important. Voyager 2 did not leave the solar system in the gravitational sense. It had crossed beyond the heliosphere, the bubble produced by the solar wind and the sun's magnetic influence. The distant Oort cloud, whose objects remain bound to the sun, may begin hundreds of times farther out. At Voyager 2's speed, reaching the inner part of that cloud will take centuries, and moving beyond its outer edge could take tens of thousands of years. But the real achievement was more significant than the simplified phrase, left the solar system. Voyager 2 had become the first spacecraft to carry a functioning plasma instrument directly across the boundary between the sun's domain and the space between stars. Voyager 1 had crossed first in 2012, but its equivalent plasma instrument had stopped operating decades earlier. Scientists had been forced to reconstruct that crossing indirectly, using particle counts, magnetic fields, and plasma waves triggered by disturbances from the sun. Voyager 2 arrived with the instrument researchers had been waiting for. It did not merely announce that a boundary existed. It measured the boundary as it passed through. NASA. The spacecraft was never designed for this moment. When Voyager 2 launched from Cape Canaveral on August 20th, 1977, its official task was to explore giant planets. Engineers built it for a mission expected to last about 5 years. Its computers possessed less memory than devices now discarded without a thought. Its commands were stored and executed by hardware created before the modern internet, before GPS became ordinary, and before many of the scientists who would later operate it were born. Yet the spacecraft carried an opportunity that would not return for another 176 years. Jupiter, Saturn, Uranus, and Neptune were arranged so that a probe could use the gravity of one planet to reach the next. Each encounter would bend the spacecraft's path and increase its speed, turning the outer solar system into a chain of gravitational slingshots. Voyager 2 reached Jupiter in 1979. It examined the planet's violent atmosphere, its moons, and its immense magnetic environment. It passed Saturn in 1981, where mission controllers made a decision that separated its future from Voyager 1. Voyager 1 followed a path optimized for a close encounter with Titan, Saturn's largest moon. That trajectory sent it upward and away from the plane of the planets. Voyager 2 was directed onward. In 1986, it became the first spacecraft to visit Uranus. It discovered new moons, new rings, a magnetic field tilted into a geometry unlike anything expected, and an atmosphere that looked quiet from a distance but concealed powerful motion. 3 years later, Voyager 2 reached Neptune. It found supersonic winds, a great dark spot, delicate rings, and the active moon Triton releasing dark plumes above a frozen surface. No spacecraft has returned to Uranus or Neptune since. NASA science. When Voyager 2 completed the Neptune flyby in August 1989, its planetary mission was effectively over. The cameras eventually went dark. Instruments designed to study planetary atmospheres, rings, and surfaces were shut down to conserve electricity. The probe was redirected toward a different target, one no telescope could photograph as a solid object, the edge of the sun's influence. This was not a destination with coordinates carved into a map. Scientists knew the sun released a wind. They knew that wind should collide with gas and magnetic fields, filling the space between stars. They knew some kind of boundary had to exist. They did not know exactly where it was. They did not know how thick it would be. They did not know whether it would be stable, turbulent, folded, porous, or constantly moving. Voyager 2 began traveling toward a place defined largely by equations. To understand what it eventually found, the word space has to be corrected. Space is not empty. Between the planets, the sun releases protons, electrons, magnetic fields, and waves. Between the stars, thin material also exists. Neutral atoms, charged particles, dust, cosmic rays, and magnetic fields left by processes unfolding across the galaxy. The sun sits inside this interstellar environment while moving through the Milky Way. At the same time, the solar wind expands outward at hundreds of kilometers per second. Near Earth, that wind can disturb satellites, compress the planet's magnetic field, and help create auroras. Farther out, it continues beyond Mars, Jupiter, Saturn, Uranus, Neptune, and the Kuiper Belt. Distance weakens it. The solar wind spreads across an ever larger volume. Its density falls. Eventually, the pressure of the interstellar medium becomes strong enough to resist it. The first major transition is the termination shock. This is where the solar wind, which had been moving faster than the waves that carry pressure through the plasma, slows abruptly below that characteristic speed. It does not stop. It becomes compressed, heated, and redirected. Beyond the termination shock lies the heliosheath. The heliosheath is the disturbed outer layer of the solar bubble. Solar plasma still dominates, but it is no longer racing freely away from the sun. It has been slowed and forced to respond to the pressure of the surrounding interstellar material. Magnetic fields pile up, particle populations change, flows become distorted. Then comes the heliopause. The heliopause is the boundary where solar plasma gives way to interstellar plasma. It is often described like the skin of a bubble, but that image can be misleading. A soap bubble has a visible surface with air on both sides. The heliopause is a boundary within plasma and magnetic fields, shaped by pressure, solar activity, charge exchange, turbulence, and the sun's motion through the local interstellar environment. It can move. The sun follows an activity cycle lasting roughly 11 years. During more active periods, it sends stronger disturbances outward. During quieter periods, pressure changes. Those variations can travel through the heliosphere for months or years before reaching its edge. The boundary can expand, contract, ripple, and respond long after the event that disturbed it occurred near the Sun. The heliosphere breathes. Voyager 1 and Voyager 2 approached this breathing structure from different directions. Voyager 1 traveled into the northern side of the heliosphere. Voyager 2 moved through the southern side and closer to what researchers describe as a flank of the bubble. The difference mattered before either spacecraft reached interstellar space. Voyager 1 crossed the termination shock in 2004 at approximately 94 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun. Voyager 2 crossed the same type of shock in 2007 at roughly 84 astronomical units. A difference of about 10 astronomical units is larger than the average distance between the Sun and Saturn. The boundary was not spherical. Voyager 2 proved that the southern side of the solar bubble was pushed inward relative to the region sampled by Voyager 1. The interstellar magnetic field, differences in solar wind pressure, and the overall geometry of the heliosphere were distorting the structure. The solar system's protective bubble was not a perfect globe. It was shaped by the environment through which it moved. After the termination shock, Voyager 2 spent more than 11 years crossing the heliosheath. That region alone was wider than the distance from the Sun to Uranus. During those years, the spacecraft recorded flows that turned sideways, particle intensities that rose and fell, magnetic structures, pressure fronts, and changes that did not match the simpler models developed before direct measurements existed. The closer Voyager 2 moved toward the heliopause, the less the boundary behaved like a fixed wall waiting in one location. Researchers watched the data for signs that the crossing was approaching. They had the experience of Voyager 1, but they could not assume the second encounter would look identical. Voyager 1 had passed through strange precursor regions where some particles disappeared and returned. It encountered magnetic structures that suggested the spacecraft was near the edge without immediately proving it had crossed. Voyager 2 approached under different solar conditions, at a different latitude, and through a different part of the bubble. In late 2018, the signals began to change. The cosmic ray subsystem measured an increase in galactic cosmic rays. These are high-energy particles accelerated by violent events beyond the solar system, including supernova explosions and other powerful astrophysical processes. The heliosphere blocks or redirects a substantial fraction of this radiation. As a spacecraft moves beyond the Sun's protective bubble, the galactic particle intensity should rise. At the same time, the low-energy charged particle instrument saw particles associated with the heliosphere decline. One population was entering. Another was disappearing. The spacecraft appeared to be approaching the shoreline. Then came November 5th. Voyager 2's plasma science experiment contained 4 detector cups. 3 faced generally toward the Sun and were positioned to measure the outward solar wind. A 4th pointed in another direction and had been useful during planetary encounters and later measurements. The instrument did not photograph particles. Charged particles entering the cups produced tiny electrical currents. From those currents, researchers could calculate properties such as density, speed, temperature, pressure, and direction. For decades, the sunward cups had detected plasma flowing outward. On November 5th, that flow fell sharply to background levels. Afterward, the instrument found no continuing solar wind flow around the spacecraft. That was the direct measurement Voyager 1 had been unable to provide. At almost the same time, the cosmic ray subsystem recorded a sharp rise in galactic cosmic rays. The low-energy charged particle detector saw heliospheric ions collapse. The magnetometer measured a stronger field. 4 independent systems were describing one transition from different physical perspectives. The particles changed. The plasma changed, The magnetic environment changed. Voyager 2 had passed through the heliopause at approximately 119 astronomical units from the Sun, around 11 billion miles from Earth. NASA, the signal confirming that event did not reach mission control immediately. Radio waves travel at the speed of light, but even light needs hours to cross the distance between Voyager 2 and Earth. When the spacecraft transmitted a measurement, the event described by that measurement had already become history long before the Deep Space Network received it. There was no joystick response. No real-time intervention was possible. Earth could only listen to the past. When NASA announced the crossing in December 2018, the milestone appeared simple. Voyager 2 had joined Voyager 1 in interstellar space. Humanity now had 2 operating probes beyond the heliosphere. The data released afterward made the event much stranger. The first surprise concerned the boundary itself. A viewer imagining the heliopause might picture an abrupt dividing line, solar material on one side, interstellar material on the other. Voyager 2 did observe a sharp main transition, but the surrounding region contained structure extending across an enormous distance. Before the final crossing, the plasma instrument recorded changes across a broad boundary region roughly 1.5 astronomical units wide. That is more than the distance from Earth to the Sun. Within that region, the solar plasma slowed, heated, and compressed as it approached the heliopause. Then a much thinner layer appeared immediately before the spacecraft entered interstellar space. The edge had an approach zone. It was not merely a line. The plasma was piling up. Inside the heliosphere, Voyager 2 detected a slight increase in plasma density near the boundary. That suggested the solar material was being compressed against the inside of the heliopause. Imagine traffic approaching a narrowing road. Cars slow, spacing decreases, and the density rises before the bottleneck. But the interstellar side showed compression as well. Voyager 1 had already found that the plasma immediately outside the heliosphere was denser than some researchers expected for the undisturbed local interstellar medium. Voyager 2 confirmed a dramatic transition. Its plasma wave measurements indicated that electron density beyond the heliopause increased by about a factor of 20 compared with values characteristic of the heliosheath. The spacecraft had not entered ordinary empty space. It had entered denser plasma pressed against the outside of the solar bubble. The sun's influence had ended in one sense, but its presence was still shaping the environment beyond the boundary. That created a more complex picture. The heliosphere was pushing outward against interstellar material. The interstellar medium was pressing inward. Plasma appeared compressed on both sides, as though the boundary were a moving contact surface within a much larger region of interaction. Voyager 2 was outside the heliosphere. It was not yet in completely undisturbed interstellar space. The second surprise was temperature. Inside the heliosphere, plasma in the heliosheath is extremely hot but thin. Temperature in a plasma does not mean the spacecraft would feel heat like an object inside an oven. The particles are sparse, but individual particles can carry high energies. Outside the heliopause, the interstellar plasma is denser and colder than the plasma inside. That broad expectation was correct. The exact measurement was not. Voyager 2 found that the very local interstellar plasma was warmer than models had predicted. It was still colder than the heliosheath plasma, but not as cold as the surrounding interstellar environment was expected to be. Something had heated or compressed it. The simplest explanation was that material was accumulating around the heliosphere. Compression raises temperature. The solar bubble moving through the interstellar medium and expanding against it could create a disturbed layer beyond its own formal edge. But the details were not settled. The instruments had encountered only 2 paths through a structure larger than the planetary system. Voyager 1 sampled one location, Voyager 2 sampled another. From those two narrow tracks, scientists were trying to understand the shape, pressure, and behavior of an object tens of billions of kilometers across. It was like placing two thermometers in different locations along an ocean coastline and attempting to reconstruct the shape of the entire continent. The third surprise was leakage. The heliopause protects the inner solar system from much of the galactic cosmic radiation arriving from outside. Voyager 1's measurements indicated that the heliosphere excludes more than 70% of some of that radiation. The boundary therefore acts partly like a shield, but a shield is not necessarily sealed. Voyager 2's low-energy particle measurements showed a trickle of particles originating inside the heliosphere escaping into interstellar space. The solar bubble was leaking. The finding did not mean the boundary had holes, like a punctured metal wall. Charged particles interact with magnetic fields. If field lines connect, reconnect, fold, or become turbulent near the heliopause, particles can follow paths across regions that appear separated in a simpler model. Voyager 2 crossed closer to the flank of the heliosphere than Voyager 1. That region appeared more porous. The shape and orientation of the magnetic fields may have allowed heliospheric particles to slip outward more easily. The boundary did not simply stop matter, it filtered matter. Different particles behave differently depending on their energy, direction, and relationship with the surrounding magnetic field. Some disappeared sharply, some increased, some leaked across, some formed a thin boundary layer outside the heliopause. The cosmic shoreline was selective, then came the magnetic mystery. Before Voyager 1 crossed the heliopause, many models predicted that the magnetic field direction would change noticeably. Inside the heliosphere, the magnetic field is carried outward and twisted by the sun's rotation into a vast spiral. Outside lies the local interstellar magnetic field, shaped by the galaxy and the material surrounding the solar system. Two different sources should produce two differently oriented fields. Yet when Voyager 1 crossed into interstellar space, the field grew stronger, without rotating as dramatically as expected. The direction outside remained surprisingly close to the direction inside. One spacecraft could have encountered an unusual local structure. One path could have crossed a folded boundary. One measurement could have represented coincidence. Voyager 2 removed that comfort. 6 years later, in another part of the heliosphere, its magnetometer found the same broad alignment. The field outside the heliopause was again approximately parallel to the field inside. The result did not mean the two magnetic fields were identical or that no boundary existed. Particle and plasma measurements proved that Voyager 2 had changed environments, but the directional similarity suggested that the heliosphere and the interstellar magnetic field were interacting in a way that forced alignment near the boundary. The external field may drape around the heliosphere. Imagine water flowing around the bow of a ship. Streamlines bend around the obstacle. In a similar way, interstellar magnetic field lines can be distorted as they encounter the solar bubble. Near the heliopause, the field may be turned into an orientation resembling the field inside. But this answer opened another question. How far does the draping extend? Voyager 2 was outside the heliopause, but still close enough for the sun-shaped obstacle behind it to influence the magnetic environment. The field it measured might not represent pristine interstellar space. It could represent interstellar space bent, compressed, and heated by the heliosphere. The probe had crossed the official border. The border had not stopped affecting it. NASA Jet Propulsion Laboratory, JPL. That reversal changed the meaning of interstellar space. The phrase sounds like a destination. Cross the heliopause, and the spacecraft enters the untouched galaxy. Voyager 2 showed that the transition is not so clean. The heliosphere creates an extended disturbance around itself. The surrounding medium presses against it. Magnetic fields bend, plasma piles up, particles cross in both directions. The sun's influence does not end at one mathematical surface. It fades through interaction. This helps explain why Voyager 1 and Voyager 2 did not experience identical crossings. Voyager 1 encountered precursor regions before its final transition. Particle intensities changed in stages. Researchers debated for months whether the spacecraft had truly crossed. Voyager 2's main particle changes were sharper and lacked some of those earlier flux structures. The two spacecraft crossed during different phases of solar activity. They approached different sides of a moving boundary. They traveled along trajectories separated by billions of kilometers, yet the heliopause distances were surprisingly similar. Voyager 1 crossed at about 121.6 astronomical units. Voyager 2 crossed at about 119 astronomical units. The difference was only a few astronomical units despite the spacecraft approaching in different directions and at different times in the solar cycle. This similarity was not easy to reconcile with the earlier termination shock measurements. The termination shock had been much closer to the Sun along Voyager 2's path. That had shown a pronounced north-south asymmetry. The heliopause crossings, however, occurred at more comparable distances. The thickness of the heliosheath was therefore different along the two paths. Voyager 2 crossed the termination shock closer to the Sun, but traveled through a wider heliosheath. Voyager 1 crossed the termination shock farther out, but reached the heliopause after a narrower passage through the sheath. The bubble was not merely squashed. Its internal layers changed thickness. The Sun's boundary system behaved like a dynamic atmosphere, not a rigid shell. Models had to account for solar pressure pulses moving outward over years. They had to include charge exchange, in which charged particles capture electrons from neutral atoms and change the way energy and momentum move through the boundary. They had to include turbulence, magnetic reconnection, and asymmetries produced by the interstellar field. The heliosphere was a machine made of flows. Voyager 2 had inserted one instrument package into that machine and allowed it to be carried through. Then the spacecraft began detecting what came after the crossing. Interstellar space was not silent. The plasma wave subsystem could listen for oscillations in the surrounding charged material. It did not record sound traveling through ordinary air. It measured electric field changes produced by plasma waves. The frequency of those waves allowed scientists to estimate electron density. Some waves were triggered by disturbances that began at the Sun. A solar eruption can launch a shock through the solar wind. That shock travels past the planets, through the heliosheath, and eventually into the local interstellar medium. By the time it reaches Voyager, the eruption responsible may have occurred more than a year earlier. The spacecraft then detects the interstellar plasma responding to a message sent outward by the Sun. Even beyond the heliopause, solar storms continue to arrive. The Sun no longer surrounds Voyager 2 with solar wind, but it can still strike the surrounding interstellar plasma with pressure waves. These events reveal density, generate oscillations, and show that the region outside the heliosphere is active rather than static. The probe crossed into the space between stars and continued hearing the Sun behind it. This was one of the deeper consequences of the mission. The heliopause was not a place where solar influence became exactly zero. It was where the dominant plasma population changed. Gravity continued, light continued, radio signals continued, shocks continued. The magnetic disturbance created by the heliosphere continued. Different definitions produced different edges. There was an edge of outward flowing solar plasma. there was an edge of the region dominated by solar magnetic fields. There was a much more distant edge of objects gravitationally bound to the sun. There was no single wall labeled "End of the Solar System." Voyager 2 had crossed the most important boundary for heliophysics, but not the final boundary of the sun. The distinction made the discovery more interesting, not less. What Voyager 2 entered was unknown, not because scientists had no models, but because no model could substitute for direct measurement. Telescopes near Earth can study the heliosphere indirectly. NASA's Interstellar Boundary Explorer, known as IBEX, maps energetic neutral atoms created far away and provides a global picture of interactions at the edge. The Interstellar Mapping and Acceleration Probe is designed to improve that remote view, but remote sensing and direct sampling answer different questions. IBEX can map the sky, Voyager can touch one point. A global map can reveal broad structure but blur small local details. A spacecraft can measure the local plasma precisely but cannot see the entire bubble. Scientists need both perspectives, and Voyager 2 provided the direct plasma measurements no other mission possessed. The achievement depended on an instrument built in the 1970s surviving long enough to encounter a region its designers could only anticipate. That survival was not automatic. Voyager 2 is powered by 3 radioisotope thermoelectric generators. These systems use heat from the radioactive decay of plutonium-238 and convert part of that heat into electricity. They contain no rechargeable fuel tank and no solar panels capable of working at such distances. Their output declines as the plutonium decays and as the thermoelectric materials age. The spacecraft loses roughly 4 watts of available power each year. 4 watts sounds small. Across decades, it becomes fatal. Every instrument, heater, computer, transmitter, and attitude control system competes for a shrinking electrical budget. Engineers have shut down cameras, heaters, and scientific instruments one by one. They have allowed parts of the spacecraft to operate at temperatures far below the levels considered safe when Voyager left Earth, and the hardware continued working. The deeper Voyager 2 moved into interstellar space, the more the mission became a struggle between scientific value and electrical survival. The plasma science instrument that confirmed the 2018 crossing eventually became one of the systems sacrificed. By 2024, its orientation meant it could collect its most useful interstellar flow data only during occasional spacecraft turns. Its power consumption remained constant while its scientific return had become limited. On September 26, 2024, engineers transmitted a command through NASA's Deep Space Network to switch it off. The command required about 19 hours to reach the spacecraft. The confirmation required another 19 hours to return. For almost 2 days, no one on Earth could know with certainty whether the aging probe had executed the instructions safely. It did. The instrument that had directly watched the solar wind vanish was now silent. That shutdown carried a strange finality. Voyager 2 remained in interstellar space, but humanity had deliberately turned off the device that had made its crossing unique. The decision was not an admission of failure. Saving those watts allowed other instruments to continue measuring magnetic fields, plasma waves, and energetic particles. The mission was trading one sense to preserve the others. In March 2025, the low-energy charged particle instrument was also shut down to conserve power. That detector had helped reveal the collapse of heliospheric ions and the leakage of particles beyond the heliopause. Its rotating scan mechanism had operated for nearly half a century. By 2026, Voyager 2's magnetometer, plasma wave subsystem, and cosmic ray subsystem remained listed as operating, while NASA prepared additional power management steps. The cosmic ray subsystem was next in the planned shutdown sequence. Engineers were also testing a more ambitious energy-saving strategy intended to replace certain powered functions with lower power alternatives and keep at least part of the spacecraft alive longer. NASA science. The irony was unavoidable. Voyager 2 had finally reached the environment it was uniquely positioned to study, just as its ability to study that environment began disappearing. Every year carried it farther from the heliopause. Every year offered cleaner measurements of the local interstellar medium. Every year removed electrical power. The spacecraft was entering better scientific territory while losing the instruments needed to examine it. This created the final open question. What would Voyager 2 have found if it could continue operating for another 50 years? The region near the heliopause is disturbed. As the probe moves farther away, the density, temperature, magnetic orientation, turbulence, and particle populations may gradually become more representative of the undisturbed local interstellar medium. The magnetic field might rotate away from its boundary-aligned direction. Plasma compression might decrease. New pressure fronts could arrive from the Sun or the galaxy. The two Voyagers might encounter different structures and reveal how far the heliosphere's disturbance extends, but the spacecraft does not have 50 years of electrical power. No replacement is close behind it. When Voyager 2's final science instrument falls silent, direct measurements along its path will stop. The spacecraft will not stop. Its motion does not depend on electricity. The momentum acquired from its launch and planetary encounters will carry it onward. Systems may freeze. The transmitter will fail. The antenna will no longer remain pointed toward Earth. The signal will disappear beneath the background noise. Voyager 2 will continue through interstellar space as a dark object. Its golden record will remain attached. The copper disk contains sounds, music, images encoded in analog form, greetings in many languages, and information intended to describe the world that launched it. The record was never expected to be found soon. Space is too large, stars too widely separated, and the spacecraft too small. Its more immediate message was never the record, it was the data. The probe revealed that the solar bubble is compressed, asymmetric, layered, and porous. It confirmed that interstellar plasma just outside the heliopause is denser than plasma inside the heliosheath. It showed that the plasma is colder than the solar material, yet warmer than expected for an undisturbed region. It detected particles escaping from the heliosphere. It confirmed the unexpected alignment of magnetic fields on opposite sides of the boundary. Each result altered the image of the edge. The heliopause was not a sealed shell. It was not a perfect sphere. It was not motionless. It was not the end of all solar influence. It was a living interface between a star and a galaxy. That is what happened after Voyager 2 crossed into unknown space. The unknown did not become empty. It became crowded with interactions. Solar particles were escaping outward. Galactic particles were pressing inward. Magnetic fields were bending around the bubble. Plasma was accumulating on both sides. Ancient radiation from violent events in the Milky Way was striking the spacecraft more intensely than before. Shocks launched by the Sun were continuing across a boundary that the solar wind itself could no longer cross in the same form. The farther Voyager traveled from home, the more clearly it measured the shape of home. That may be the deepest reversal in the story. Voyager 2 entered interstellar space to study what lies beyond the Sun. Instead, the first thing it discovered was how the Sun changes the space around it. A star does not exist as a bright sphere isolated in darkness. It blows material outward. It carries magnetic fields. It blocks radiation It displaces interstellar plasma. It creates a protective cavity and drags that cavity through the galaxy. The planets live inside that moving structure without seeing its walls. But one crossing was enough to destroy the simplest picture. Scientists once spoke of the heliopause as though reaching it would reveal a clean division. Solar wind here, interstellar medium there. Voyager 2 found a boundary with memory. The plasma inside remembered pressure from the interstellar medium. The plasma outside remembered the presence of the heliosphere. The magnetic field remembered how it had been bent around the bubble. The escaping particles remembered pathways connecting both sides. The border carried information about everything pressing against it. Voyager 2 was built to visit planets, but its final planetary flyby occurred in 1989. Most of its existence since then has been spent traveling through darkness toward measurements that could not be guaranteed. The engineers who assembled it could test electronics, antennas, thrusters, and instruments. They could calculate trajectories. They could not reproduce 40 years of radiation, cold, power loss, and distance before launch. Its computers did not become faster. Its antenna did not grow larger. Its power source did not renew itself. The distance simply increased. The signal arriving at Earth became unimaginably weak. NASA's Deep Space Network used enormous antennas and sensitive receivers to separate that signal from cosmic noise. The data rate fell far below what modern devices transmit casually. Yet inside that faint stream were measurements from a region no other functioning spacecraft had reached. A few bits could describe the magnetic field beyond the sun. A tone could confirm that the probe was alive. A change in frequency could reveal the density of interstellar plasma. Humanity did not need a high-definition image of the heliopause because there was no surface to photograph. The story existed in numbers. Particle counts fell. Cosmic rays rose. Plasma flow vanished. Density jumped. The field strengthened but barely turned. Each measurement looked small on a graph. Together they marked the first direct passage of a working plasma detector from a star's atmosphere into the material between stars. Voyager 2 did not find an alien signal. It did not encounter a hidden planet. It did not strike an invisible wall. Nothing about its crossing required unknown physics. The surprise was that known physics, acting across enormous scales, created a boundary more complicated than the models built before any spacecraft reached it. That is how exploration usually changes science. The universe does not always overturn physical law. More often, it reveals that the law can produce structures richer than limited observations had suggested. The heliopause existed because pressure had to balance somewhere. The shock existed because the solar wind had to slow. The interstellar magnetic field had to bend around the solar bubble. Particles had to respond to fields and turbulence. Every ingredient was familiar. The combination was not. Voyager 2 turned an abstract border into a measured environment. It found that the edge had thickness. It found that the outside was already disturbed. It found that separation could coexist with connection. It found that a protective bubble could also leak. It found that crossing into interstellar space did not mean leaving the sun entirely behind. Even now, Voyager 2 continues moving through a region shaped partly by the object it escaped. The sun remains one of the brighter stars in its sky, though the spacecraft has no operating camera to see it. Radio commands still reach its antenna. Solar eruptions can still send disturbances past its instruments. Gravity still pulls backward, though not strongly enough to reverse its flight. The spacecraft is beyond the solar wind, but still inside a story controlled by the sun. Eventually, that will change. The heliosphere's disturbances will weaken with distance. The magnetic field may settle toward the undisturbed interstellar orientation. the sun's shocks will spread and fade. Voyager 2 will pass into regions no mission team can monitor after the power is gone. Tens of thousands of years from now, it will still be moving. The planets will have completed countless orbits. Earth's continents will shift. Human civilizations may be unrecognizable or absent. The probe will carry no active beacon, but the crossing already happened. For one moment in November 2018, an instrument built before the first space shuttle flight watched the solar wind disappear. A machine designed for 5 years had survived for more than 4 decades. It was nearly 18 billion kilometers from Earth, operating on declining radioactive power and transmitting through a dish pointed toward a planet too distant to distinguish from the surrounding stars. The 3 cups facing the sun went quiet. That silence was the measurement. It meant the stream of particles that had surrounded the spacecraft since launch was gone. Voyager 2 had moved beyond the atmosphere of its star and entered plasma created elsewhere in the galaxy. Then the supposed emptiness began answering. It answered with greater density. It answered with unexpected heat. It answered with cosmic radiation. It answered with particles leaking across the boundary. It answered with a magnetic field pointing in a direction that should have changed more than it did. The unknown was not waiting beyond a wall. The unknown was the wall itself. Voyager 2 crossed it once. Humanity is still trying to understand what crossed back in the data.